The thing I've always loved about engineering is that the concepts that you first learn in the classroom end up shaping the way that you view the physical world. I became hooked as a second-year student sitting in my statics class at Fort Lewis College in Durango, listening to my very exciting young teacher talk about forces and moments. Until that point, I had no idea that engineering was for me. I was just pursuing it till I found something I liked better, because I loved Legos growing up, but I was terrible at spelling, but decent at math. The following year, I found myself sitting in the thermodynamics class, and I was absolutely astounded that much of the core infrastructure that we depend on today, like power plants and industrial sites, could be governed by a few thermodynamic principles. First, that energy is always conserved, and second, that energy flows in a certain direction unless you add it to the system. I was struck by the power of this realization and wanted to have my own impact on the systems that are so valuable to the world as we know it today. But it was not lost on me that many of these same integral systems, like power plants and industrial sites, are responsible for the growing CO2 emissions and contributing to global climate change. These systems took decades to build, they required a significant amount of capital investment and engineering effort, and they're very integral to life today as we know it. So the challenge becomes, how do we reduce emissions without abandoning the infrastructure that is so integral to our modern world? This question inspired me to pursue a master's degree at Colorado State University, where I examined the intersection between decarbonization, power systems, and thermodynamics. It was at Colorado State University that I discovered a young company that was using core thermodynamic principles to freeze the CO2 out of the flue gas of industrial sites and power plants so that it wasn't emitted to the atmosphere. At FrostCC, what makes our approach interesting from a thermodynamic perspective is that we use the flue gas itself as a refrigerant to freeze CO2. We compress and expand the flue gas through a reverse Brayton refrigeration cycle, which uses turbomachinery to expand the gas, similar to how a gas turbine works. In this case, the Brayton system works much better because it relies on sensible cooling, which matches the heat profile of the gas as it freezes. Pressurizing the flue gas within the Brayton cycle also has some additional benefits. It increases the frosting temperature, which increases cycle efficiency. It also increases upstream water knockout through condensation. And finally, it decreases the total footprint and cost of the plant by decreasing equipment sizes due to the more dense flow rate. The result is a carbon capture system that's mostly built from conventional turbomachinery and heat exchangers. As a process engineer at FrostCC, I'm lucky to contribute to the design and testing of these systems. I get to see it develop from first principles through tests and eventually to a commercial product. I love seeing the system come together from modeling and cycle evaluation to full-scale testing and pilot-scale operations. Climate change is going to require some serious engineering, and for those of us passionate about thermodynamics, this is a great opportunity to apply what we love doing to a problem that really matters. I'd love to hear your thoughts. Please give us a like and a comment to keep the conversation going.